let's talk about something different. Another example. I have one more example to share with you in this lecture. Okay, so example 3. This example won't require as much visualization, so hopefully it'll be a little bit easier. So let's take G to be the special orthogonal group, SON, and X to be the sphere in Rn. Okay, so, well, what can we say about the orbit space? So here, X mod G, well, in this case, it's actually quite boring. This is a single point. There's only one orbit. I mean, for any vector on the sphere, there's an isometry taking it to some other vector. I mean, this is kind of similar, or this is a more general statement than homework 2, number 5, where you showed for any 2 points on the 2 sphere, there's a rotation taking one to the other. And so in general, you can do this in higher dimensions as well. Okay, so this is, so here the quotient space, this is kind of boring. Well, a single point, doesn't get more boring than that. But there is an interesting quotient space that we can get from this, which is a partition of G. So now let's consider there's a map from SON to the sphere, just given by evaluating on a single point. So let's fix E1 to be the unit vector like this, and look at the map that just sends a matrix, orthogonal matrix, to its value on E1. So this is, one way to think about this is the first column of A. So given a matrix A, we just read off its first column. And that will give us a point on the sphere. So the action being transitive, so when the orbit is a single point, we say the action is transitive, meaning you can get from any point to any other point by the action. So this action transitive means that this map, let me call it Q. Q is surjective. And well, this implies that Q is a quotient map by something we proved last week. Because, well, SON is compact and the sphere is Hausdorff. So then what we see, let me just make room. I want to fit this here. So this gives us a description of the sphere as a partition, as a quotient of, or as a quotient space of the special orthogonal group. And we'll want to identify what that quotient space is. So this is Q inverse of X, X in Sn minus 1. So this partition, so this is a partition of SON. And I mean, what is this partition saying? The partition elements are given a point on the sphere. So I have, I don't know, E1 here, and then I have some other point, X. The partition is, what are all the orthogonal matrices which send E1 to X? So what are all the orthogonal matrices whose first column is this vector X? But note, so observe that if you have two orthogonal matrices which send E1 to the same vector, then, well, B inverse A sends E1 to itself. 2 points belong in the same, 2 points of SON belong in the same element of the partition if and only if, well, we have this condition, which we can rewrite as, so B inverse of A, this matrix has the form, it's a block matrix where here C is in SON minus 1. So what you conclude from this, that the partition P of SON, this is the partition into left, right cosets of SON minus 1 in SON. Okay, so the conclusion is this coset space is topologically equivalent to Sn minus 1. Okay. Okay, so although in this case we're looking at G acting on X, the action is transitive, so the orbit space is boring, but we get this other quotient space. So that we see that we get a description of X as a coset space of G mod, a subgroup of G, which is here the stabilizer of SON. Lucky. Okay. So I'd like to use this now to prove the following fact, which is that the orthogonal group, special orthogonal group, is connected for every n. So you proved a special case of this on homework, and so now I want to describe why this is true in general. And before, yeah, so for this, in order to prove this, we need one lemma, which goes as follows. So I'm going to leave this to you as an exercise. In fact, this is Armstrong's exercise, Armstrong 4.29. So it says if you have G acting on X, then the quotient map from X to the orbit space is an open map. Okay, so we'll see why this is useful in a second. So now let's prove the corollary.
All right. So proof of the corollary. So we'll do this by induction on n. So the base case, well, n equals 1, SO1. Well, okay, so let's think about this. SO1, this is matrices, 1 by 1 matrices, so that A transpose A is 1, and the determinant of A, which is just A, is 1. So this is just a single point. Or we also know in the case n equals 2 that this is SO2 is connected by a homework. Connected by homework. Okay, so we could take that as the base case if you want. Okay, so now let's do the induction step. So we're going to assume SON minus 1 is connected and show SON is also connected. And so we'll do this by contradiction. Suppose that SON, this is a union of two open subsets which are non-empty and disjoint. So let me not write that, but okay, suppose we have this. And now let's consider the quotient map. SON to this coset space, which we know is the sphere. So by the lemma, Q is an open map. So Q of U and Q of V are open. And the n minus 1 sphere is the union of them. So Sn minus 1 is connected. So what can we possibly make of this? Well, this means that, well, we know each of these is non-empty and that they're disjoint. No, that their union is everything. But the thing that can't be true is that they're disjoint. So there exists some point X in the intersection. This X must exist because otherwise Sn minus 1 would be disconnected, which we know it is connected. Okay, and so without loss of generality, we can take X to be E1. Let me not harp on this statement. You can think about that. So now let's consider U prime, which is U intersect SON minus 1, and V prime, which is V intersect SON minus 1. So let me draw a picture here. So we have SON, and inside of here we have SON minus 1, some subset. And we have these two U and V. whose union is everything. So something like this. And well, U prime and V prime are just these intersections with SON. So here's U prime, and here's V prime. Now, we're assuming that SON minus 1 is connected. So this is where we're going to derive a contradiction. So what we know, U prime and V prime are disjoint, because U and V are, and their union is all of SON minus 1. So all we need to get a contradiction is to show that their intersection is I don't know, let's see. All we need to get a contradiction is to show that they're both non-empty. But why is that true? Well, we have this point X here, which is a point, oh, sorry, we know that, so we have E1, which is in Q of U intersect Q of V. So that means there's a point in, right, but what does it mean for E1 to be in Q of U? So let me write this here. So E1 is in Q of U. This means that there exists an element of U so that A of E1 is E1. But this means that this A is in SO n minus 1 and also in U, which is our U prime. Okay, so that's saying that there's at least one point in U prime, and similarly there's at least one point in V prime. So these are non-empty because E1 is in Q of U and E1 is in Q of V. Okay, so this means that SON minus 1 is disconnected, which is a contradiction. Okay, so that's the proof. Okay, so today we're gonna start a new topic. So we've now finished with the point set topology part of the course, and the next part of the course is going to be about the fundamental group, which is an important topological invariant. So to sort of motivate the discussion, let's start by considering the following example. So let's consider the disk, a closed disk, D2, and the annulus, S, circle across an interval. And well, the basic question is, what makes the disk different from the annulus? And well, there's various ways to answer this question. One answer you might give is remembering back into earlier in the semester, the Euler number. These two have different Euler numbers. So if, well, This isn't the main answer I want to give, so let me just explain this quickly. So the Euler number of the disk is 1, and the Euler number of the annulus is 0. Okay, so that's a fine answer. But, well, when you draw these two, maybe the most obvious thing you say is, well, the annulus has a hole and the disk doesn't. And that's something that we're going to make precise with the fundamental group. So one way to say this is properties of loops. So specifically on the disk, every loop can be deformed to a constant loop. So if you start with some arbitrary loop, it doesn't necessarily have to be embedded. I mean, it could be something, complicated. Loop means it ends where it starts. But let me draw it kind of nice for now. So it's something like this. So the claim is it can be deformed to a constant. So you can just sort of like shrink it down until it's a constant loop. Like this. But that's different than the annulus. So on the annulus, well, there exist loops that can't be deformed to a constant. I mean, there are some loops that you can. So if we draw the annulus again, then, well, if I draw some loop like this, then I can deform that to a constant by the same sort of picture. But there are loops that you can't. So something like this, for example. Of course, this requires proof, and eventually we'll give such a proof. But for now, we're just going to work sort of intuitively. You imagine that, well, since there's that hole there, you can't deform this loop that goes once around to a constant map. Right. So the way we make this precise, so we make the concept of deforming precise with homotopy, the concept of homotopy. Yeah, so let me give a few definitions before giving you the definition of homotopy. Okay, so first, a loop. Sorry, let's start with some notation. So let's let X be a space, and P and X a base point. So we just fix some point. And we say that, so a loop based at P is a continuous map from the interval into X, which starts and stops at P. So f of 0 is f of 1 is P. And we say two loops F0 and F1 are homotopic, if there exists well, let me go ahead and just give you the full definition. If there exists a map like this, so that so so we have two coordinates here. Let's call them S and T. We want Fs0 to be F0, Fs1 to be F1. This map should be continuous. And we also want F 0t to be P and F of 1t to be P. So the picture, there's a reasonable way to picture this. So we have a map of, F is a map of the unit square into X. And so here's the S direction and here's the T direction. And for T equals 0, this is, if we just restrict to here, this is the map F0. Here, this is the map F1 for T is 1. That's what we have here. And then when S is either 0 or 1, so that's on these two edges, we're just doing the constant map P. Okay, so this is a homotopy. So this is what's called a homotopy. This is an interpolation. This is a deformation from the map F0 into the map F1. So in X, you have some sort of picture, like you have F1, and then there's some other map F0 inside here, and the homotopy is a way to interpolate between these two. And interpolate between maps which are based at P, between loops based at P. Okay, so this is how we make precise the idea of deforming one map into another. So for example, well, every loop in the disk based at 0 is homotopic to a constant. So if we start with, let's say, G, maybe it's bad to call this little f, since little f was the notation for a loop. I'm going to change this to capital F for the homotopy. So, okay. All right. Yeah, so let's take little f to be some loop, any loop. Into the disk, any loop based at P, based at 0. And then we can define f of st to be t times f of s. So what does this do? So we see that at time 1, of this homotopy, we have the map just little f, so that's good. At time 0, we're doing 0 times f of s, and so that's just the constant map, 0. And then for any t at time, so this loop, the loop at time t starts at 0 and also ends at 0. So capital F of 1t is t times f of 1, which is t times 0 is 0. Okay, so this is like a straight line path, whatever the loop is. So it starts at 0, and well, you just move points along the loop inward along straight lines. Okay. All right. So we're going to write f sim g if f and g are homotopic. And we'll see eventually, or this is not hard to show, that this is an equivalence relation. Which is to say that, well, any map is homotopic to itself just by the constant homotopy, do nothing. If f is homotopic to g, then g is homotopic to f. That's not so hard to see. And then there's transitivity. G homotopic to h implies f is homotopic to h. Also not hard to see. Right, so reflexivity, symmetry, and transitivity. So this is what is needed to be an equivalence relation. And we'll write pi 1 of xp for the set of loops based at p up to this equivalence relation. So for example, we've just shown that on the disk, there's one equivalence class. Since every loop is homotopic to a constant. So pi 1 of the disk, base point 0 is just a single point. On the other hand, on the annulus, there are many equivalence classes. Let me just draw a few of them for you. Well, okay, so there's the constant, where you just, the constant map, the constant loop at the base point. Let's say this is our base point P. There's the loop I drew before that goes once around in this way. There's another loop which has the same image, but you just go the other way around. And this is different. This requires proof, but these are different loops. These are not homotopic. And then there's more interesting things you could do, like you could go around twice. counterclockwise, and that's different. Or you can go around twice clockwise, and so on. So there's lots of equivalence classes in this case. And in fact, later we'll show that there's one equivalence class for every integer. So there's a bijection like this, which is given roughly by the winding number. So the thing that distinguishes the different equivalence classes is how many times you go around the circle, and you have to keep track of whether it's clockwise or counterclockwise. Okay. Right, so this notation, well, okay, so let's see. The next comment, sorry, let me clean this up a little bit. The next comment is that this set pi1 of x loops based at p up to homotopy, this can be made into a group. Under the operation of concatenation. So namely, so the way this works is if you're given f and g, well, so let me just draw a picture first. So here's x, and I have two loops, f like this, and then g. They're both based at p. Well, if I want to look at the product of these loops, well, one thing I can do is, so the concatenation, you just do first f and then do g. So given maps like this, from the interval into x based at p, we define the concatenation f star of g. And the way this works is, well, this is supposed to be a map defined on 0, 1 on the interval. So we want to do f twice as fast, so we're going to do f at twice the speed and then do g at twice the speed so that we can fit them both in the interval. So in a formula, we can do that like this. No, f twice the speed. So we do that for s between 1/2 and 1 and 0, 0 and 1/2. And then we want g to start at time 1/2 and go at twice the speed. So, well, this is a function that does that. Right. So the concatenation, it's a map that first you do f and then you do g, and well, yeah, you do them at twice the speed. Right. So the key thing here is, right, so there's this group structure, and we'll make all of this, we'll prove some of the things that I'm saying next time, that this actually gives you a group structure. And so we call pi1 of x p the fundamental group. Of x based at p. So in fact, on this slide, when I said pi1 is z, this is actually an isomorphism of groups. Okay, and later, we'll show that this group is a topological invariant. So topological equivalent spaces have the same fundamental group, invariant. And it's independent of the choice of P. If X is connected. If X is connected. So for example, so e.g. pi1 of the disk is trivial and pi1 of the annulus is Z, this implies that, well, these two are not topologically equivalent. Okay. So I want to finish now. Okay, so I want to do a few, well, let me do a new page. So I want to finish with some intuitive computations, which we'll see in more details later. So the first, well, okay, so I've explained this one, or let me do it this way. Pi1 of R2, this is 0. So this is similar to the disk. Any loop, you can just deform it to a constant, just like we did for the disk. Pi1 of the circle is Z. We'll prove this. And this is similar to the annulus. So it's the homotopy classes are, the loops up to homotopy are determined by how many times you go around the circle. Another example, the fundamental group of the torus is Z squared. In fact, this computation follows from the previous one. So the fundamental group of a product we'll see is isomorphic to the product of fundamental groups. And so here, generators, we have these two loops here. And you can see concretely that they, so let's call these A and B. You can see that they commute from our description of the torus as a quotient of the square. So here we have A, B, A, and B. You see that, well, the loop that first does B and then does A is homotopic to the loop that first does A and then does B. And the homotopy is staring at you right here in the face. You just interpolate like this. So this picture is showing you that A concatenate B is B concatenate A. So indeed, the generators here commute. Okay. Now, something interesting we could do is take the torus and remove a disk. So now we have, so I draw that like this. We still have loops A and B as before. So A and B. And these still generate. But now this argument here doesn't work. We don't have a nice homotopy between A and B. And in fact, in this case, A and B don't commute. And this group is what's called a free group. So this is the free group on two generators. So elements of this group are just words in A and B, similar to this complement closure situation where you just write words down, but here there's no relations. So you just have A's and B's, and yeah, okay. So this, as it turns out, is what you get if you remove this disk. One more example, the fundamental group of the projective plane. So remember that we had this description of the projective plane as you'd start with a circle and then you attach a disk. So the picture of that was like this. So the way you attach the disk, it goes around the circle twice. Let's call that A, and then you have A again. So this picture gives you a homotopy between A and A inverse. So A is A inverse, which is to say that A squared is 1. So from this, you might guess that this group is isomorphic to Z mod 2Z, and we'll show that eventually. Okay, so we'll stop there, and next time we'll start to make some of this precise.